Introduction to Determinants. In Chapter 3, we're going to look at a special number that gets assigned to a square matrix called a determinant. And we'll also look at some of the related applications, including later in the chapter, how to find the area of a parallelogram and how to find the volume of a parallelepiped. In order to calculate determinants, we're going to need a little bit of notation. And we're going to start with this matrix that you see here, A sub ij, which is essentially a submatrix of the original matrix. If we start with a matrix A, like you see here, the resulting matrix A sub ij is the matrix that you get if you delete the ith row and the jth column. In the example, we're going to look at A sub 2, 3, which means that I'm going to take out the second row and the third column, and then the entries that show up in neither that row nor that column get put into the matrix A sub 2, 3. So we end up with the matrix 1, 2, 4, 9, 10, 12, 13, 14, 15. Before we get into determinants for larger matrices, let's go back and recall what we had earlier for the determinants of the small 2 by 2 and 1 by 1 matrices. For the matrix with rows A, B, and C, D, the determinant is calculated by calculating the product of the entries on the main diagonal AD minus the entries on the opposite diagonal BC. And for the determinant of a 1 by 1 matrix, it's just the single entry. Finally, to the main definition here, we can calculate the determinant for any size square matrix. For n greater than or equal to 2, the determinant of an n by n square matrix A, where the entries are given as little a sub ij, the determinant is given by determinant A equals little a sub 1, 1 times the determinant of the submatrix big A sub 1, 1 minus little a sub 1, 2 times the determinant of the submatrix big A sub 1, 2, etc., etc. Alternating signs here. So the first one's positive, the second one's subtraction, so it's negative, the third one's going to be positive, it'll be addition, and so on. All the way till you get to the end of the row here. And it may be positive or negative depending on whether n is odd or even here. But then that last entry will be of the form little a sub 1n times determinant of the submatrix big A sub 1n. And we can write it in sigma sub notation as the sum as j goes from 1 to n of negative 1 to the power 1 plus j times a little a sub 1j times the determinant of the submatrix big A sub 1j. This definition of determinant will of course make the best sense after we've looked at an example, because it's a pretty tough definition, but I think once we work a couple of examples, it'll be second nature here. So let's take a look at this. To calculate the determinant of this 3 by 3 square matrix A, here's what we're going to do. We're going to go across the first row, which has entries 1, 2, and 0. And at each step, multiply the entry times the submatrix that you get when you eliminate that particular entry's row and column. And of course, for determinant, you also have to alternate sign for each term. So let's take a look at this. So let's start with the first entry here, which is a 1. It's in the first row, first column, so let's eliminate the rest of the first row and the rest of the first column and look at the resulting leftover entries as a 2 by 2 matrix in its own right. So what we'll have here is we're going to have the entry 1 times the determinant of that submatrix, where the submatrix is going to have rows negative 1, 2, and 0, 1. Now we're going to do the same thing for the rest of the first row, but remember, as we go along here, we have to alternate sign, and I'm going to reflect that with a little bit of a color change here as we go on to the next one. So now we're going to move on to the entry 2 in the first row, and remember, this is going to be a negative entry this time. We're going to eliminate the rest of the first row and the rest of the second column, because now we're in the first row, second column entry. and we're going to subtract, so it'll be minus 2 times the determinant of the resulting submatrix from those leftover entries. So it'll be minus 2 times the determinant of the 2 by 2 matrix with rows 3, 2, and 2, 1. And then let's move on to the third and last entry of this row. This time we're going to use that entry 0. We have swung back now to a positive signed term as far as the determinant goes. This entry is in the first row, third column, so we're going to eliminate the rest of the first row and the rest of the third column. And we're going to multiply this entry times the determinant of the resulting submatrix, which really isn't going to be that important because you're multiplying it by 0 anyway, so it's going to end up being 0. So now we have the structure for this determinant. All we have to do to really finish this off now is to find the 2 by 2 determinants and then perform the multiplications and additions and subtractions. It turns out that the determinant of the first matrix is -1 because when you look at those diagonals there, the main diagonal gives you -1, subtract the other diagonal, which is 0, and you end up with -1. The determinant for that second submatrix there is going to be 3 times 1 minus 2 times 2, which will be -1. And on that third matrix, you're going to have 3 times 0 minus the quantity -1 times 2, which will end up being 2. So plug in the values for those three determinants, multiply together your numbers, do the appropriate additions and subtractions, and we end up here with a determinant whose value is 1. There is a notation that helps us abbreviate this a little bit so that we don't have to write determinant every time. Instead of writing determinant of a matrix that's in square brackets, to denote that we want to have a determinant, instead of writing determinant of the matrix in square brackets, we can just write the matrix itself inside of a pair of vertical bars. And that indicates that we would like to calculate the determinant rather than just have the matrix. So the calculation that we just performed, where we went across the first row to calculate the determinant, it can be redescribed using this new notation as you see below. That 3 by 3 determinant equals 1 times a 2 by 2 determinant minus 2 times a 2 by 2 determinant plus 0 times a 2 by 2 determinant. It gets a little bit tricky. You have to recall the difference at all times between a matrix in square brackets, which is just a matrix, and a matrix in vertical bars, which indicates a determinant. This process whereby we calculate a determinant by going across a row and reducing it into products of smaller determinants is sometimes called a cofactor expansion. And to be specific here, the cofactor, the ij cofactor, which will be denoted by c sub ij, that's going to be -1 to the power I plus j times the determinant of the submatrix big A sub ij, which is the matrix A with row I and column j deleted. So another way to rewrite the determinant that we calculated in our first example would be that this 3 by 3 determinant is 1 times the cofactor C11 plus 2 times the cofactor C12 plus 0 times the cofactor C13. And you might say, well, where did the signs go? The cofactors already take care of the signs for you with that -1 to the I plus j power. That -1 alternating between -1 and 1 will take care of all the signs that you need. In our definition of determinant, we essentially did a cofactor expansion across the first row. Theorem 1, on the other hand, will give us a whole lot more flexibility, and it'll allow us to calculate the determinant in a much more expedient way, because the determinant of a square n by n matrix A can be computed by a cofactor expansion across any row of the matrix or down any column of the matrix. So you can pick any single row or any single column, do a cofactor for that row or column, a cofactor expansion for that row or column, and you'll calculate the determinant. This turns out to be handy because if you have a row or a column that has lots and lots of zeros in it, that's a terrific choice for your cofactor expansion because it'll really make things pretty easy. And in terms of performing the cofactor expansion, you just have to remember that your cofactors are going to have these alternating signs. And so to process this idea of -1 to the I plus j power, it's usually a lot simpler to just think of it in terms of this alternating sign matrix, where you start with a plus sign in the first row, first column entry, and then just alternate between pluses and minuses like a checkerboard. So the sign of your cofactor is just going to be given by the appropriate signs of the pluses and minuses in this checkerboard's matrix. Let's compute the determinant of the same matrix that we used in our first example. This is the matrix A with rows 1, 2, 0, 3, -1, 2, and 2, 0, 1. So it's the same matrix we used before. Let's calculate the determinant of this matrix using a cofactor expansion, except this time let's use the third column. Earlier we used the first row, here let's use the third column. If we use the third column, the first entry there is a 0. If you follow that plus and minus checkerboard type matrix, this is going to be a positively signed entry. So what we're going to do here is you're going to do 0 times the determinant of the corresponding submatrix. Now if this entry is positive, all we have to do for the rest of the entries in this cofactor expansion is to just keep alternating sign. So the next one here will be negative. And since we're working our way down the third column, the next entry is the 2 that resides in the second row, third column. So we eliminate the rest of the second row and the rest of the third column. And so this is a negatively signed entry, so we're going to do -2 times the determinant of the corresponding submatrix, which will have rows -1, 2, and 2, 0. And then for the last entry in this cofactor expansion, we're going to have a positively termed entry. We have an entry here that's in the third row, third column, so eliminate the rest of the third row and the rest of the third column. As we indicated a second ago, this is a positive entry in our cofactor expansion, so this is going to be +1 times the determinant of the resulting submatrix. And if you work this out, this is going to be 0 for the first part of the cofactor expansion. When you get to the next one, you're going to have -2 times -4, which will be 8. And then you're going to have +1 times -7. So you end up with essentially 0 plus 8 minus 7, which is 1. And we're getting the very same determinant, of course, that we had when we calculated this example the first time. Because, as we indicated in Theorem 1, the determinant is independent of which cofactor expansion you choose. Let's calculate the determinant of a 4x4 matrix. Normally you do a cofactor expansion, turning the 4x4 matrix into a cofactor expansion of 3x3 matrices, and then you could get the 3x3 determinants by doing cofactor expansions into 2x2 determinants. So it's a pretty lengthy process, but we're lucky in this aspect. We get to choose whichever row or column we want here, And we have a column here which has a single non-zero entry. And so that's clearly the right choice, since we can choose any row or column we want for our cofactor expansion. So we're definitely going to pick first column here for our cofactor expansion. So for my cofactor expansion here, I'm going to take the first column, and I'll have to start with the entry in first row, first column, which will be 1 times the determinant of the resulting 3 by 3 submatrix. Then the rest of the cofactor expansion is going to be 0 times this, 0 times that, and 0 times this. So those entries all fall away. And all we have now is essentially a 3 by 3 determinant to calculate. We can calculate this 3 by 3 determinant using cofactor expansion. To calculate the 3 by 3 determinant using cofactor expansion, again, we want to pick the row or column that has the most zeros in it. And in this case, this is going to be the first column of the matrix 2, 1, 5, 0, 2, 1, 0, 3, 5, because that first column is 2, 0, 0. And so when we do the cofactor expansion there, we're going to have 2 times the determinant of the resulting 2 by 2 submatrix, and then some 0 entries, 0 times a 2 by 2 determinant, and another 0 times a 2 by 2 determinant, which just, again, drop out. So now we're going to have 1 times 2 times this determinant, and when you calculate the determinant, it's 10 minus 3, which is 7. So the end result here is going to be 1 times 2 times 7, which is 14. If we have a matrix that has all zeros below the main diagonal, or if it has all zeros above the main diagonal, then what we have is what's called a triangular matrix. If the matrix consists of all zeros below the main diagonal, it's called an upper triangular matrix because all the non-zero entries reside in the upper triangle of the matrix. And if we have all zeros above the main diagonal, it's called a lower triangular matrix because all of the non-zero entries reside in the triangle in the lower half of the matrix. As it turns out, the determinants of these triangular matrices are rather easy to calculate because the cofactor expansions have so many zeros when we make the right choice. In fact, the determinant of a triangular matrix is very easy to calculate. When you play with some of these cofactor expansions, you'll figure out that when we calculate the determinant of one of these triangular matrices, the determinant is simply the product of the entries on the main diagonal that goes from the upper left-hand corner down to the lower right-hand corner. For example, if we have this upper triangular matrix that's shown here, a 4 by 4 matrix, and we'd like to calculate the determinant of it, because it's an upper triangular matrix, to calculate the determinant, all I have to do is multiply the entries on the main diagonal, which are 2, 1, negative 3, and 4. Multiply those 4 numbers together and we get negative 24, which is our determinant.